Now we are going to consider energy balance, metabolism and nutrition, with the main emphasis on energy balance. Energy balance is closely related to metabolism. Metabolism as a whole, with all the complexity of its chemical reactions, is studied in a course of biochemistry. We are going just to recall the general principles of metabolism and energy production. First, metabolism includes all the chemical and energy transformations that occur in the body, and it consists of the two opposite processes, anabolism and catabolism. These two Greek prefixes, ana and kata, can directly be translated as up and down, so that the meaning of the terms anabolism and catabolism related to metabolism is correspondingly creation of own body substances and their breakdown. Both are related to the own substances of the body. Let's see. When we have glucose, fatty acids and amino acids already absorbed from the digestive tract, we can use these substances for anabolism. From simple substances, we can produce the complex ones. From glucose, we can produce glycogen. Fatty acids can be converted to the complex triacylglycerols, and from amino acids, we can make the proteins. These all processes are of anabolism. For the catabolism, the own substances of the body, such as glycogen, are converted back to simple substances. From glycogen, glucose is formed then. Triacylglycerols of fat tissue can be converted back to fatty acids, and proteins can be split into amino acids. All these processes of own substances breakdown related to the catabolism. Let's see again what is anabolism. This is the process of the complex substances formation, such as proteins, fats, and complex carbohydrates, from simpler molecules. And also it includes the synthesis of energy-rich phosphate compounds, which can store energy. As for catabolism, it's the opposite process of the breakdown of body substance, complex body substances into simple ones. And it results in stepwise liberation of energy. Let's consider the functions of the nutritional substances. They all perform different functions. Basically, we have two functions for nutritional substances. One is formation of body structures, or the so-called plastic function. And the other function is giving us energy. And all substances, proteins, fats, and carbohydrates, perform these two functions in different proportion. As for proteins, of course, we mostly consist of proteins. These substances are involved into structures formation predominantly. There is even the popular definition of life. Life is a way of protein bodies' existence. Really, we are protein bodies, and proteins form the most structures. For the energy purpose, the proteins normally are not used. They can be used actually when there is no other sources of energy. So in case of serious starvation, they have. So as for fats and carbohydrates, they perform an energy role both, but differently. Fats, of course, they are high energy substance, because each gram of fat can give us 9 kilocalories, which is compared to carbohydrates, just with their 4 kilocalories is much higher. And of course the fats are performing the energy role and to a great extent. But nevertheless, fats participate in the structural function as well. For example, fats form the fat tissue, which is included into the body structure, and provide their heat insulation, provide their mechanical protection of internal organs, and so on. But of course, the main example of the plastic structural function of fats is participation of subtype of fats, phospholipids, in formation of the biological membranes. So the energy and plastic role is performed perhaps equally. Membranes are widespread in the body, and throughout the whole body, phospholipids form these membranes, and they belong to lipids or fats. And as for carbohydrates, they function predominantly as energy. Predominantly we oxidate glucose, and many other carbohydrates are converted to glucose or to other simple carbohydrates, and they give us a lot of energy. Of course, it doesn't mean they do not participate at all in the structural function. Yes, they participate, but much less. For example, carbohydrates chains are used for labeling of intracellular proteins for their subsequent sorting and transportation to different parts of cell. Then carbohydrates are present on the surface of membrane. If you remember, the antigens of the red blood cells membrane, A and B antigens of ABO system belong to carbohydrates predominantly. And so, of course, they participate in structures formation, but their main function really is energy function. Let's recall the interconnections between the different substances' metabolism. Look, from biochemistry course, you know it well, I believe, that glucose, fatty acids, amino acids finally enter the same cycle. Pyruvic acid is formed out of glucose, or acetoacetic from fatty acids and amino acids. Finally, they form the acetyl coenzyme A and enter the cycle of energy formation in mitochondria, where stepwise liberation of energy occurs, and oxygen is used, and as a result, end products are formed, such as carbon dioxide and water. And the main result, of course, is energy. Many molecules, up to 36 molecules of ATP, can be formed out of each glucose molecule. So ADP is converted back to ATP, and macroergic bond is formed, and this is a way to store energy for its subsequent use. Energy transformations in the body. Let's see. All these food substances give us energy, and this cellular chemical energy partially is converted to ATP, but not all. Immediately, ATP is formed, but big portion, even higher than half portion of energy, becomes converted to heat. You know that there is a law of energy conservation, and energy does not disappear, just it becomes converted into different type, and this type is heat now. About 60% at least of the energy from nutritional substances, oxidation is converted to primary heat, and a lesser part is converted to ATP. This ATP then can be used for many processes listed here, such as mechanical work, processes of synthesis, membrane transport, electrical work, detoxification, and so on. All these processes use ATP energy. But then when energy is used, it becomes again converted to heat, but now it's called a secondary heat. So you can see that all the energy received from food eventually is converted into heat. There is an exclusion when we produce the so-called external work. External work can be like lifting of some objects upward, and so the energy is converted to potential energy of these objects. But usually, in many cases, we simply do not produce the external work, and so the work just refers to contractions of the muscles, and so it simply becomes converted finally into heat. Our muscles contraction finally release heat. The main ways of energy utilization. Previously you saw the list, but now the main ATP that is formed in mitochondria, used for membrane transport. Maybe it's number one process because it's included into many processes. Interaction of nervous cell in the nervous system. It also used for muscle contractions or calcium pumping back and regular pumps operation. So membrane transport is everywhere. Absorption of nutritional substances from the tract. All this uses energy for most substances. So classically it's a sodium potassium pump, but the other pumps also use energy, calcium pump, H+ pump, and so on. So this is a big part of our energy usage, maybe 40% or so. Then also synthesis of proteins in the endoplasmic reticulum requires energy, ATP. And muscle contractions. As you remember, the muscle contractions, each muscle contraction requires a lot of ATP molecules. For each sarcomere, for one cycle of interaction of actin and myosin filaments, we need one molecule of ATP. but taking into account how many sarcomeres muscles have, how many cycles per second they perform for contractions, you can imagine how many molecules of ATP must be used for muscle contractions. And don't forget that even resting state of muscles do not mean that they do not use energy, because of course their energy expenditure is less, but for resting state, maintaining of muscle tone also requires usage of ATP molecules for irregular contraction of some motor units. Energy expenditure of the body is referred to as metabolic rate when it's measured per time unit. In most cases, we measure per day, but in some cases it's necessary to measure per minute or per hour. But generally, if we need to compare metabolic rate of different persons, mostly we compare per day. So as I already said, that if external work is not performed, all the energy released by the metabolic processes finally becomes body heat. And in this case, we can understand how we measure the metabolic rate. If metabolic rate is equal to the rate of heat liberation by the body, we can measure this heat liberation, and therefore, if it's equal to metabolic rate, we can know the metabolic rate of the body. So energy used can be measured as energy liberated by the body. Metabolic rate can be very different. Metabolic rate depends on the level of physical activity to a great extent. And it can be less with light activity, it can be high with medium or high level of activity. But if we need to compare, there is a difference between people, even without physical activity. And in order to compare individual differences, regardless of physical activity level, we need to know the basal metabolic rate. Basal, here it means lower, base. And any other types of activity additionally can be added to this basal metabolic rate. And really, it's minimal energy required for performing essential body functions at rest. Why minimal here is given with asterisk? Because really we can have sometimes less energy expenditure than this minimal, which is basal metabolic rate. But this can happen only in the sleeping state. It can be less than basal metabolic rate. And we measure basal metabolic rate in the awakened state. And for awakened state, this is a minimal, really, without any asterisk, minimal energy required for maintaining the body functions. The total metabolic rate, of course, is higher than basal metabolic rate. And it includes first component, basal metabolic rate, then, of course, it includes energy expenditure for the physical activity. Then, food processing. As for food processing, I hope you understand that to get the substances present in food, we need first to chew this food, move it throughout the digestive tract, along the digestive tract. We need to secrete juices and release the enzymes that will produce reaction of digestion of these substances. Then we need to absorb the substances, and most of substances require active transport through membranes from the digestive tract. So to take the energy which is present in the food, we need to spend a little of energy for its digestion, to convert food into nutritional substances available for absorption and absorbed into blood. So food processing also requires energy. Usually not much, but it depends on the composition of food. Especially proteins have the greater energy expenditure for their digestion and absorption. So, and last, the thermoregulation processes. In case of neutral, comfortable temperature, we don't need to activate processes of thermogenesis or processes of heat loss. But in case of difference of real temperature from neutral, from comfortable, we must activate the processes of heat production or heat loss. All this requires additional energy. So you see there are many components in a total metabolic rate. And these components, let's see their ratio. The basal metabolic rate usually makes at least half of the total metabolic rate, and it can be higher in case of not high activity, physical activity. Physical activity can be increased so that it becomes the highest increase, it makes the highest increase of the metabolic rate. Food processing. Usually it makes about 8 to 10%, but for short time the protein digestion can increase metabolic rate about 30%, up to 30% of the basal metabolic rate temporarily. This additional energy expenditure, which also becomes converted to heat, is called thermogenic effect of food. But also there is other term, specific dynamic action of food. It means that food intake increases the heat generation because it results from the energy expenditure for digestion of this food. And thermoregulation, mostly of course thermogenesis, but even increased heat loss requires some additional changes in the body that require energy. Here you can see it's on the figure about 60% at rest, between 50 and 70, maybe 60% average, the contribution of the basal metabolic rate to the total metabolic rate. To the left side you can see lower level of metabolic rate, which corresponds to sleeping state. In different phases of sleep we can have different energy expenditure, but in certain phases the metabolic rate becomes even less than basal metabolic rate. In case of arousal, immediately the level of energy expenditure becomes basal metabolic rate exactly. Then there is thermic effect of food. As I said, sometimes, in most cases, it doesn't exceed 8 to 10%. Then non-exercise activity. We live with movements. We cannot, even if it's not serious physical activity, some movements occur which are necessary just to care about ourselves and so on. These all are non-exercise types of energy expenditure, and they usually take certain amount of energy usage. And of course, purposeful physical activity. Here it shows the average level without specific high activity, about 25% of the total metabolic rate. But you see the upper line made serrate, in serrate fashion, so it shows that it can be highly variable. It depends on situation, depends on person. Let's observe how many kilocalories are used by average 70 kilogram man. Average weight usually is taken as 70 kilogram. And here you will see 4 types of activity and calories. Please pay attention to calories. When this word is written with capital letter C, it's the same as kilocalories when calorie itself is with small letter. So it corresponds to kilocalories, but the word kilo is not necessary to add. You see, low level of activity is for all this listed by now. Sleeping, lying still in awakened state, sitting at rest, standing. You see, even standing or even sitting increases our energy requirement because it's necessary to maintain contracted state of certain muscles that are necessary for posture. But then walking slowly increases almost approximately twice our energy expenditure, and some lower levels of physical activity increase a little bit more. But greater activity increases greatly energy expenditure, and you see such actions like swimming, running greatly increase the energy expenditure. And especially high energy expenditure becomes in case of walking upstairs. You see, if it's made rapidly, 1,100 calories per hour it makes. But note again that it's only per hour. Usually we do not maintain walking upstairs rapidly for the whole hour. But at least you can compare, and the numbers show even per minute the ratio will be similar. So it requires great energy expenditure in this process. Let's come back to the basal metabolic rate. Why it's different for different people? There are a number of factors. The main factors that determine the basal metabolic rate of a healthy person are the 4 following factors: the age, sex, height, and body mass. As for age, we'll consider for next slide, but for sex, between men and women there is difference, and generally men have higher level of basal metabolic rate. There are few explanations for this, and including for example the androgens, they increase the oxygen requirement of the body, but also we can explain it simply by mostly higher percentage of skeletal muscle tissue of men. Skeletal muscles make contribution to the basal metabolic rate. Don't mix with the physical activity. Skeletal muscles, even at rest without physical activity, maintain their tone, and it requires energy. And greater amount of muscle tissue in the body makes requirement of greater amount of energy for maintaining the muscle tone. And so this creates the difference between men and women, number one. Height and body mass clearly increase the size of the body, and body needs more energy for maintaining the essential functions. But it's for healthy person. In case of abnormal levels of hormones, among which number one are thyroid hormones and also growth hormone, these hormones really affect the basal metabolic rate. I hope you remember that thyroid hormones functions, maybe first line was the increase of the basal metabolic rate. They increase energy expenditure by building more pump operating in the body and more active transport, and this increases the requirement in energy. So, and correspondingly, the hypothyroidism will decrease the basal metabolic rate. So, 4 factors. Normal body metabolic rate, basal metabolic rate at different ages. This figure shows the changes with age of basal metabolic rate, but note that here you don't see absolute values of basal metabolic rate. Otherwise, of course, you will see that how you can compare the basal metabolic rate of the baby with basal metabolic rate of adult. Of course, with less size of the body, the baby makes less heat, produces less heat, and uses less energy as the big body of the adult. But for comparison, here you see the values of calories per square meter of the surface area, body surface area. And here it's given per hour, but it doesn't matter. Anyway, ratio is the same. And according to this figure, you can see that maximal energy expenditure per each square meter of the surface area is in early age, in babies. And after birth, they start to decline their basal metabolic rate rapidly, and this decline reaches approximately steady level about 20 years old age. And then the level of basal metabolic rate remains more or less steady until approximately 45 years old. Then it starts to decline, but slowly, not as fast as in early age. Slowly it declines and declines, but not greatly. Note. Basal metabolic rate measurement. This is one of the most complex questions in this theme, but I hope you will understand it easily. First, it's necessary to know how we can bring the metabolic rate to its minimal for awakened state level, to make it really basal metabolic rate. So first we need to exclude, of course, the physical activity. And simply resting state will be not enough. Simply sitting, resting without physical activity, it's not enough to have basal metabolic rate measurement. It's necessary to be in a line for the tested person, to be in line position, fully relaxed muscles, and quiet emotional state. Because if person is under strong stress, with great adrenaline level, it may also increase the metabolic rate and make it higher than basal metabolic rate. But even with all these conditions followed, it's not enough to measure basal metabolic rate. You remember, we need to exclude additional energy expenditure for food digestion, because how we can compare between different people if one person had, for example, the protein food, meat, great amount of meat, and another person had only carbohydrates. The digestion of carbohydrates is much easier and takes less energy than proteins. So it will be not pure basal metabolic rate. Therefore, it's necessary to reach the situation when practically the digestive tract is free of food. it's not easy task, because usually food spends about 1 day in the digestive tract. Some types of food may pass as faster, some even take longer time. So official requirement is, but here I mentioned already awakened state. Official requirement is fasted state with no less than 12 hours after the last food intake. But actually, if it should be measured precisely, simply 12 hours is not enough. It's necessary to have previous few days only vegetable food. Therefore, we can make sure that after 12 hours, the digestive tract will be empty and processes of food digestion do not take any additional energy. Because if food was usual with proteins and with fat, and not only carbohydrates, then there will be not enough to have just 12 hours. Fortunately, these measurements are not done so often, so it's unusual mostly for research purposes. And the third condition is the thermoneutral conditions. It means that temperature should be room temperature, comfortable for the person. As for numbers, I can say about 20 degree plus minus a little bit, but you see different sources may give slightly different for few degree of Celsius values, and also it greatly depends on clothes of the person. It can be warmer or it can be light. And also it depends on individual. Some people feel normally at 18 and some people feel cold at 18 degrees. So it should be comfortable for this individual, but of course it's not very high difference, plus minus range. It's something around 20 degrees Celsius. And now, with these conditions, we can measure the basal metabolic rate. There are two entirely different methods for determination of the metabolic rate. First is direct calorimetry and another one is indirect. But first, calorimetry. I hope you'll remember easily this term for method of measurement, because we determine the metabolic rate by measurement of the heat liberated from the body. Calor, this is a Greek word for heat. So we measure the amount of heat released from the body. Calorimetry. And then, if you understand easily that direct is exactly measurement of heat, so direct calorimetry principle is clear and you cannot forget this. Direct calorimetry is simply measurement of the quantity of heat liberated from the body. Of course, technically it's not very easy process to measure the heat that is released from the body. It's necessary for the tested person to be placed into the specific chamber, which is heat-insulated chamber, large enough so that person can move somehow inside, and it should be entirely heat-insulated so that heat that is formed in this chamber can come only from the tested person's body. And this heat amount should be measured. Until now, mostly they measure it by measuring the temperature of the water that flows through the pipes. There are numerous pipes that pass through the chamber near the wall, and this water becomes warmer due to heat released by the body. And due to this warming of water, we can measure the temperature of initially supplied water and water that flows out of the chamber. So heat gain of the water is equal to heat liberation. And so by this measurement, we get the amount of heat liberated from the body or metabolic rate of the person. Let's see it on the picture. This is the heat-insulated chamber. Heat gain of the water is measured. You see temperature of water which is supplied to the chamber. Of course, the pipes are much more numerous than shown here for schematic purposes. And temperature of water that flows out is measured, and difference of temperatures shows the amount of heat liberated from the body. Also, we can notice here that there is the oxygen supply constant, because you understand the heat-insulated chamber does not allow entering of external air. So with breathing of the tested person, gradually oxygen should be decreased, CO2 with water vapors should be increased. But to avoid this, oxygen supply is constant, corresponding to the velocity of usage of this oxygen. And also you see that air goes out and it passes through the devices which eliminate excess of CO2 and excess of water vapors. So the air composition in the chamber is constant and does not become changed due to breathing activity of the person. Of course, this method is not widely used, mostly for research purposes, because it's not easy, it requires a great amount of equipment. Mostly used is another method, which is indirect calorimetry. So it's not measurement of heat directly. This calorimetry is performed with gas analysis. Full name is indirect calorimetry with gas analysis. Why? How it's performed? It's performed by measurement of oxygen consumption by the body and then determination of the amount of energy that is produced per each liter of oxygen. This is called the caloric equivalent of oxygen, or also can be called energy equivalent of oxygen. Metabolic rate, therefore, can be calculated by multiplication of caloric equivalent of oxygen, which shows how many calories are produced for each 1 liter of oxygen per 1 liter. And then we multiply by the amount of oxygen really consumed by the body. So kilocalories per time we receive by multiplication of caloric equivalent of oxygen, which shows kilocalories per 1 liter of oxygen. And then we multiply by number of these liters or parts of liters of oxygen consumed per certain time. Usually measurements are done, of course, not for the whole day. Therefore, mostly we measure for period of 1 minute. For a few minutes it's measured and calculated the mean value for 1 minute. Then it can be recalculated per hour, per day, and so on. So this is the main basis for the indirect calorimetry. And it's not very easy because caloric equivalent of oxygen is not standard constant value. It depends on type of substance which was oxidated by this oxygen. It can be different and it's necessary to find it. Caloric equivalent of oxygen. See, it's reaction of oxidation of substances looks like follows. If we oxidate glucose, if we oxidate fats, the end products are the same: carbon dioxide and water, and of course energy. So, amount of energy released by 1 liter of oxygen can be different depending on the substance. For proteins, this amount of energy is about 4.6 kilocalories per liter of oxygen. But I hope you already remember that proteins are not much used for the oxidation to receive energy. It's just known that if we oxidate, it will yield such an amount of energy. Then for fats, value is 4.69 kilocalories per liter. And for carbohydrates, it's 5.5. Of course, it can be with 3 numbers after the comma, and it will be more exact, but it's enough to remember like this. In case of average diet, or actually in case of average level of oxidation, when we oxidate fats and carbohydrates in different ratio, the mean oxygen caloric equivalent value is about 4.825 kilocalories per each liter of oxygen. You see, it's between value of fats and value of carbohydrates, between. Because we usually do not oxidate only fats or only carbohydrates. So this value I recommend to memorize for calculations. Caloric equivalent of oxygen, again, it shows the amount of energy produced by 1 liter of oxygen when this oxygen is used for oxidation of nutritional substances. But again, which substances do we oxidize? We oxidize not proteins. Proteins are used mainly for structural purposes. Negligible amount can be oxidated, but mostly we use carbohydrates and fats. And caloric equivalent of oxygen thus varies from minimal for fats, 4.69, up to maximal for carbohydrates, 5.05. To find the exact value of caloric equivalent of oxygen, we measure the ratio of CO2 produced and oxygen consumed during metabolism. So we can come back to reaction. Substance plus oxygen, and oxidation of the substance produces end products: carbon dioxide, H2O, water, and energy. And oxygen amount used and CO2 amount produced, ratio of these two volumes is different for each substance. Ratio when CO2 is divided by oxygen, remember, not oxygen above, but oxygen is in denominator. CO2 ratio to oxygen. CO2 produced and oxygen consumed. Of course, only these volumes that participate in the reaction can be used. And then values of this respiratory quotient differ depending on type of oxidized substances. See, respiratory quotient of carbohydrates is 1 exactly, and of fats it's about 0.7. Now, how we determine the respiratory quotient exactly? We measure oxygen and CO2 content in the expired air. And this exactly is the gas analysis. Do you remember? This is indirect calorimetry with gas analysis. These are measurements we do, oxygen and CO2 content in the expired air. But for calculation of respiratory quotient, we need to know how much oxygen was used. And expired air oxygen was exactly not used. But we can find how much was used because we know the initial content. And similarly, CO2, which is released, it's almost the same as produced because the initial amount is very little, 0.03%. But anyway, it's necessary to subtract this. So inspired air, oxygen and CO2 is considered standard, as we know, 20.93 for oxygen and 0.03% for CO2. So we can calculate the difference. If we subtract content of oxygen in the expired air from 20.93, we get how much oxygen was used by the body, because expired oxygen was not used from initial. Then CO2 expired, we take and subtract from this CO2 percentage which was initial in the air, which we consider 0.03. So now we receive oxygen consumed and CO2 produced as a result of reactions in the body. So we can calculate respiratory quotient as ratio of CO2 to oxygen. Here I must say that to be exact, it's not perfect respiratory quotient because sometimes, not always, but in some situations, this calculation can differ from real respiratory quotient. And so we can, to be more exact, we can say that what we calculate from the expired air, this is respiratory exchange ratio. And mostly it's equal to respiratory quotient. But it can be not equal when a person has intensive respiration, intensive lung ventilation after exercise, when the oxygen debt is paid and additional oxygen is spent. Then it can be different in case of metabolic acidosis, alkalosis, and so on. And when physical activity is not a steady level, but increasing gradually or decreasing. In these cases, it can be not very accurate measurement, and it's not the same as respiratory quotient. But in other situations, when there is no excessive exercise with non-steady level of activity, when there is no acidosis, alkalosis, in most cases, what we measure is equal to respiratory quotient. But just you should know that exactly it can be called the respiratory exchange ratio, or abbreviation RER. But now, both respiratory quotient and oxygen caloric equivalent depend on nutritional substances, which were used for oxidation. Now it's just words, but let's see. Respiratory quotient 0.7 corresponds to fats. For fats, we know caloric equivalent 4.69. Here it's more exact with not rounded. Then, if respiratory quotient is 1, we know that what was oxidated, that carbohydrates. For For carbohydrates, we know the caloric equivalent, which is 5.05, or here again it's more exact value, but it's enough to remember 5.05. And now, in real situation, we don't oxidate only fats or 100% of carbohydrates. We oxidate some certain mix of both fats and carbohydrates, and therefore respiratory quotient will take certain value between 0.7 and 1. But correspondingly, caloric equivalent will be shifted similarly from fat value minimal and becomes closer to carbohydrates value maximal, and will be somewhere between, but exactly proportionally to the change of the respiratory quotient. So, as a result, there are numerous tables, we need not even to calculate these, tables already developed of correspondence. For each value of the respiratory quotient, we can find in the tables corresponding value of the caloric equivalent of oxygen. Again, minimal value characterizes fats oxidation, maximal value carbohydrates. Similarly, caloric equivalent of oxygen is minimal for fats and maximal for carbohydrates. And if we use for oxidation both substances, the value of caloric equivalent is somewhere between this end value, these limits. And so these tables are developed. You see again, minimal respiratory quotient 0.7 and minimal caloric equivalent 4.69. Maximal value of caloric equivalent is of respiratory quotient is 1 and caloric equivalent is 5.05. So, and all intermediate values here are given, and correspondingly caloric equivalent will occupy the place between these values for fats and for carbohydrates. And note, here you can see the value which is considered to be mean caloric equivalent of oxygen. It's not perfectly middle-sized, but 4.825 is considered to be mean amount of kilocalories per 1 liter of oxygen, in case when person has a usual mix of fats and carbohydrates and these substances are oxidated. So now let's make it clear why this ratio exists exactly, 0.7 or 1. Let's start from carbohydrates. Why it's 1? It can be easily deduced from biochemistry. This is equation of oxidation of glucose molecule. And to make it equal, balanced to two sides, we need to place the following coefficients. So 1 molecule of glucose for its oxidation requires 6 oxygen molecules. As a result, 6 molecules of CO2 are produced, as well as 6 water molecules. But we are interested in CO2 and O2 ratio. So 6 molecules of CO2, 6 molecules of oxygen. According to physics laws, you know that the same number of molecules provide the same volume regardless of the type of gas. Doesn't matter that one gas is carbon dioxide and another gas is oxygen. The same amount of molecules and volumes are equal. Therefore, you can easily see that ratio of volumes of CO2 and O2 is 1. So, for carbohydrates, the respiratory quotient is 1. Then let's say for fats. For fats, it's not always a standard the same. Just for example, we take more or less typical fat, tripalmitin. And you can predict that oxygen is necessary in much more quantities for oxidation because final products are the same, CO2 and H2O. But look, for molecule of fat, oxygen is not often met. You see, much less oxygen as compared to glucose. Therefore, to produce the same substances as a result, CO2 and H2O, we need to add many molecules of oxygen. Make it equal. You see, these coefficients should be placed. And now you see that ratio of CO2 produced to oxygen used is different. It's approximately about 0.7. Much more oxygen is required to produce the same molecules that we make out of glucose. And that's why fat have much higher oxygen usage for their oxidation. And now you can understand why Glucose is the most economical and most widespread substrate for energy. Glucose gives only 4 kilocalories per 1 gram, while fats gives 9 kilocalories. But if we measure amount of energy released by 1 liter of oxygen per molecule of glucose or per molecule of fat, or per 1 gram, sorry. So difference is in favor to glucose, 505. If glucose gives 4 kilocalories per gram, the value of caloric equivalent of oxygen, 505, shows that it's enough to oxidate by 1 liter of oxygen more than 1 gram of glucose, because gram gives 4 kilocalories and we have more than 5. While fats give 9 kilocalories per gram, but its caloric equivalent of fat is 4.69, which is a little bit more than half of amount of energy present in each gram. And it shows that a little bit more than half of gram only is oxidated by each liter of oxygen. So now two subtypes of indirect calorimetry. One is more complex and another one is very simple. Indirect calorimetry with full gas analysis requires measurement of the both factors, oxygen consumption and CO2 production. So we calculate real respiratory quotient or respiratory exchange ratio, if you remember, to be exact. And then, using value of respiratory quotient, we find the corresponding value of caloric equivalent of oxygen from the tables. And then we calculate the energy expenditure by the following way, like it was said in the beginning of explanation. Oxygen caloric equivalent multiplied by oxygen consumption. Caloric equivalent shows how many kilocalories we can get from 1 liter of oxygen, and then we multiply by number of liters spent by body. And so we can get kilocalories per minute energy expenditure. This is most precise method. But there is indirect calorimetry with partial gas analysis, and it's much easier. In this case, what is partial analysis? We don't measure these two factors, but which one is really necessary anyway? Let's come back to previous slide. You see oxygen consumption to the right angle beneath. It's always necessary for calculation. Without this, we cannot do any calculations. So really oxygen consumption is the one only value measured really. And CO2 measurement is not done. And we don't calculate respiratory quotient, we don't find a caloric equivalent because we simply take the standard value of this index. Simply 4.825 kilocalories per each liter of oxygen. Without measurements, we decide that it's low probability that person oxidated only fats or only carbohydrates. And exact proportion can be slightly different, but more or less, it will be close to the average value of oxygen caloric equivalent, which we know already without any measurements. Of course, in reality, it can be slightly different, and sometimes even not slightly, but for certain purposes, this great precision is not required, and it's enough to use this simple value. Then we can simply multiply this already known value, average value, by measured oxygen consumption. And so it's an easier way for measurement. Of course, oxygen consumption still is necessary to measure. Now let's finish the calculations and let's consider overall energy requirements. Let's again take the average man of 70 kilograms. And basal metabolic rate for such a man is approximately 1,650 kilocalories, more or less depending on age and body height, but mostly it's about like this. So this is basal metabolic rate, and mostly it varies between 1,500 up to 1,700 kilocalories. This is basal metabolic rate without any activity. Then food processing, approximately about 200 kilocalories added. Then maintaining the muscle tone just for sitting already increases up to 2,000. And daily energy requirement, if no physical serious activity is performed, it's already 2,000 kilocalories, or it can be said with capital letter C, simply calories. So it already makes 2000. But mostly we do some more activity than only sitting. I hope that you don't sit always. So average physical activity increases it some more. And total and daily requirement usually for such a man of 70 kg with a moderate level of activity is about 2,500, 2,700 kilocalories daily. And what for we determine this? Mostly we determine this to know how much calories we need daily, because our energy input and energy output should be equal. In cases when the body is healthy and there is no overweight or underweight. So now we need to estimate the body mass, because before decision of how much calories we need to get, we need to know, do we need constant balance or it's necessary to correct something. And body mass is the objective index for the evaluation of energy income and expenditure of energy balance. One of the common methods of estimation of body mass is calculation of the BMI, body mass index. It's calculated by the following way. Body mass taken in kilograms is divided by height, but height in a square, and taken in meters. So that, for example, if someone's height is 170 centimeters, we take 1.7 and take a square, 1.7 by 1.7. So notice, in meters, not in centimeters. And this index varies from minimally 18.5, maximally 25, normally. These are normal limits. But not everyone can be normal. Sometimes it happens that someone's body mass index is less than 18.5. It corresponds to a decreased body mass. And if it's higher than 25, it's an increased body mass. And here, unfortunately, we have sometimes much more than simply 25, so there is little differentiation. From 25 to 30, it's overweight. And above 30, it's already called obesity. Obesity, excessive accumulation of fat. So, and on the basis of estimation of body mass, we can see it is necessary just to maintain balance, or it's necessary to make income and expenditure of energy not equal. Income should exceed expenditure of energy when we need to increase body mass, and what happens more often, it's necessary to decrease energy income and increase energy expenditure in order to decrease body mass back to normal. For this we have regulation in the body, but not always it works properly. But for healthy person, normally it works. Of course, we are going to study in digestive system physiology which factors contribute to limitation of food intake for each intake of food each time. It's short-term regulation. Now we are not going to consider this in detail. We are going to consider only long-term food intake and body mass correspondingly regulation. And it's based on secretion of such a hormone that is called leptin. And leptin is secreted by adipose tissue of the body, by fat cells. And it's arranged in such a way that the more fat cells are present, the more fat is accumulated in the fat cells, the more leptin they produce. And leptin decreases appetite. It modulates the activity of hypothalamic centers. If you remember, there is hunger center and satiety center. So let's start from the moment. For example, food intake exceeds the energy expenditure. For a healthy person, it can happen sometimes. For example, the period of great holidays when we have less activity and we have many meals, and it may happen temporarily, even for a healthy person, food intake can be higher than energy expenditure. In this case, fat deposition increases in the adipose tissue, but high fat deposition corresponds to high leptin secretion. Leptin, released into blood, reaches the hypothalamus and changes the activity of the integrating center, which means the center of hunger and center of satiety, with high activity of hunger center and less activity of satiety. with high activity of satiety center and less activity of the hunger center, so that appetite is decreased, and as a result, food intake decreases. Saturation with food comes earlier, and the person starts to eat less. So, food intake decreases, and finally it results in restoration of correspondence. And opposite, if food intake is decreased, sometimes it happens in nervous situations, some examination, but examination can be different. But actually, any case when food intake is decreased and energy expenditure is increased, so there is no balance. In this case, adipose tissue fat deposition decreases, leptin secretion correspondingly decreases as well, and hypothalamic center's activity is changed to the favor of hunger center activity. And then food intake in the next period of compensation increases, and again body mass comes back to normal. Unfortunately, all this nice regulation system doesn't work always easily, but in healthy person it must work normally. And therefore it's not easy to change the body mass. Even we can say the set point of the mass. It's harder to move from the middle point which is established for a healthy person. Let's consider the basic principles of healthy nutrition. This is the last section of the lecture, and basic principle number 1 is energy income should be equal to energy expenditure. The balance of income and output of energy. Of course, it all should be maintained in case of body mass normal. So the total caloric value of daily food should be equal to the energy daily expenditures. Again, when body mass is normal and everything is normal. So depending on the level of physical activity, daily caloric value of food can vary from 2,000 or even some less sometimes, because 2,000 we calculated for 70 kilogram man. It can be for a little girl, for smaller girl it can be much less. But usually it's about 2,000, but depending on level of physical activity can be even up to 5,000. But it's only for cases of very high level of activity, heavy work, physical work. But on average about up to about 3,000. Calculation of energy obtained from food. I already mentioned these values many times, but now let's see it on the screen. The average physiologically available energy in food substances is carbohydrates 4 kilocalories per 1 gram, fats 9 kilocalories per 1 gram, and proteins 4 kilocalories. Note that this is named physiologically available energy. In some sources you can find slightly different numbers like 4.1, 4.3, 9 point something. This is after point numbers can be achieved when food substances are fully oxidated, like it can happen inside the calorimetric bomb. It's called a specific device where it's burned or chemically oxidated until full oxidation. In our body, we cannot reach 100% of oxidation of food substances because at least their absorption does not make 100%. Carbohydrates are absorbed close to reality, about 98%, but fats have rather high, but proteins are absorbed not fully. And taking into account this not full 100% absorption of substances from food, the caloric values are rounded to these 4, 9, and 4. And if you see any label of products in the store, some food, you can find the values of caloric. And caloric values of food exactly corresponding to composition, when per each 100 gram the composition is given. So many proteins, so many fats, so many carbohydrates. Corresponding values of calories can be easily calculated, and they will coincide if you multiply gram of proteins per 100 gram by 4 grams of fats by 9 and carbohydrates by 4, and total resulting caloric value of this type of food will coincide exactly, because this always adopted taking the physiologically available amount of energy present in each gram of nutritional substances. It must be remained, it's easy. Then, this was the first principle. Now the second, ratio of main food substances and their quantity calculation. Ratio, proteins to fats and carbohydrates, is based on proteins. Actually, we need proteins, of course, but the amount of proteins we need daily is less than for fats and carbohydrates. And proteins we take as 1 for this ratio. And therefore, the total ratio is 1 to something more and to something much more. Fats we need a little bit more than proteins in gram. And carbohydrates we need much more. Our diet should be based on carbohydrates. And in some sources it can be just 4.6 and some sources up to 5 in this ratio. So 1 protein amount taken as 1, 1.2 for fats and up to 5 for carbohydrates, respectively. This ratio also you should remember. And on the basis of this ratio, we can easily calculate the amount of fats and carbohydrates necessary per day if we know the amount of proteins necessary for a day. And what about daily intake of proteins recommended? It should be about 0.8 to 1 gram per kilogram. And even it was better if I corrected this. Lower limit should be even 0.75. 75, it's more adopted correspondingly to this. 0.8 also not bad, and up to 1, but exactly 1 gram is not recommended for healthy people. It's for some type of, some different groups of people. And actually 0.75, 0.8 is it's correct according to recommendation of the World Health Organization. They require the intake of proteins less than 1 gram per kilogram. 0.75, 0.8, don't look only on the screen values, but listen, 0.75 minimal level. It's called protein optimum. It means that we have enough proteins and we don't only replace the degraded proteins, but also we can form new substances out of these amino acids received from proteins, optimum proteins. By a higher value, an upper limit, can be given for proteins which are not fully saturated with all amino acids necessary. We'll consider next slides. So the least amount to be taken, this is called protein minimum, is about half of a gram per kilogram, just 0.5. But it means that it's enough just to substitute the degraded proteins each day. Obligatory loss of proteins, it's called. Each day, number of protein molecules become too old and requires to be substituted by new ones. And this obligatory loss of proteins requires the 0.5 gram per kilogram. So it's not enough for a healthy person. But clearly, if the amount of proteins taken is less than 0.5, it will be serious protein starvation. Number 3. If we come back again, if we calculated the protein amount on the basis of this recommendation, let's say 0.75 per kilogram, multiplied by kilogram, we know the amount of proteins necessary. Then we can easily produce fat requirement by multiplication of protein requirement by 1.2, and carbohydrates amount can be multiplied, protein value can be multiplied by 4.6 or even by 5. So we can calculate how many grams we need of both fats and carbohydrates on the basis of protein requirement calculated. It was about quantity of nutritional substances. Now the principle number 3, quality of nutritional substances. And now we consider what about proteins. Why in some cases it's enough just 0.75 and sometimes it's necessary to take even 1 gram per kilogram or more. Because proteins are not equal. The best proteins are called complete, and it means that they contain all essential amino acids. Best examples of the complete proteins are meat, fish, egg, and dairy products, mostly animal origin products. Egg is shown here differently from others because egg protein is considered to be the standard ideal protein as according to World Health Organization. The egg protein contains clearly all the necessary amino acids. Fats. So for proteins, again, I'll come back. If the proteins are not complete, they do not contain at least one amino acid, it's already not complete. The total amount of proteins must be increased, because if we have variety of proteins, in total they can cover the requirement in essential amino acids. But anyway, it's better to use complete proteins as well as maybe not complete alone as well. Fats. Fats also are different. Among fatty acids, number of fatty acids can be produced in the body, and there is number of essential fatty acids that cannot be synthesized in the body. They are called essential fatty acids, and they are polyunsaturated with double bonds. And main ones are linoleic and linoleic. Also, arachidonic acid belong to this group of essential amino acids, fatty acids. But in contrast to proteins, which are best of the animal origin, the fats with the best composition are vegetable fats, vegetable oils. In the text you'll have the description. The best vegetable oils that contain a number of these are such oils as, for example, the linseed oil, one of the best sources of the necessary linolenic acid, which cannot be produced in the body. And the other examples also are given. Carbohydrates. Carbohydrates also can be divided into simple and complex compounds. And complex are much better because they cannot be digested quickly and absorbed quickly. When there is great absorption and immediate absorption into blood, great increase in concentration of glucose requires great release of insulin, and as a result it provides conversion of part of carbohydrates into fat, and generally it's not good when great fluctuation of glucose occur in the blood. And complex compounds, complex carbohydrates, are not so quickly digested and gradually absorbed. They don't give great rise of the glucose concentration in blood, and they consider to be the best. And of course, simple carbohydrates can give much more calories than we need, and not such a great saturation or satiety sensation that we need. And fourth principle includes necessary intake of vitamins, minerals, trace elements. Here I'm not going to give values because they are given in biochemistry course, but it's always should be remembered that these substances must be present. Then, something that we do not digest at all, this is the dietary fibers. But we need a certain amount of dietary fibers. Perhaps number one reason is because the normal intestinal bacteria will flourish on these dietary fibers. And normal intestinal bacteria provide us with good immunity, good digestive processes, and so on. But also dietary fibers stimulate peristalsis. They may absorb on their surface the excess of cholesterol, and so eliminate this from the body, excrete, and some other harmful substances. Also, I hope everyone remembers about it, we need sufficient amount of water, which should be equal to the loss of water daily. And approximately it can be at least, actually not for 2.5, it can be at least 2 liters, but it depends on person habits, how much water is lost from the body, and depends on conditions, because for example, hot weather increases loss of water and so on. But certain amount of water balance should be maintained. And all this is end of the lecture. Thank you for your attention.